Okay, so what do I mean by quantized energy? Well, quantized energy means that we've got very discrete packets of energy. So the smallest quantity of energy that can be emitted or absorbed. So we can look at two different pictures here. Okay, in this picture, I have a slope, and my ball is just going to keep rolling down that slope. Okay, I can stop it at any point by putting up a barrier. Now, on my staircase, though, my ball can only go from one stair to the next, to the next, to the next. I can't hover the ball in between any of the stairs. Just like when you're walking up and down stairs, you can only go up, you can only go down. You can't hover in between two of the stairs. Okay? So this is what we mean by quantized energy. That where our electrons are, they're in these discrete areas, and we can only go up or back down. We can't hover in the middle. So that example that I showed with that 984 kilojoules per mole of energy, if it takes 984 kilojoules to go up to the next energy level, you have to have at least 984 kilojoules of energy to get it to promote. If only 983 kilojoules of energy entered the atom, the electron would not promote. Because just like we can't hover in midair, electrons cannot hover in between these energy levels. They're discrete quantized levels. If we were in class, I would do my demo for this where I would climb up on a stool and then jump back down to illustrate that I can't hover in between the floor and the stool when I'm going up or when I'm going back down. Okay, and so we get, energy absorbed. Okay, we have the right amount of energy, we jump up and we hang out, then we emit. If we have even more energy, we can jump up to an even higher level, we can hang out there, and then we drop back down and we emit. And so remember, low energy, we're going to have a large wavelength. High energy, we'll have a short wavelength. Okay? We have three different regions that we can get the stuff from. We've got the ultraviolet region, the infrared region, and then what we can see is our visible region. Okay? It's right there. And so notice that for UV, we drop to n equals 1. So we drop back down to the first energy level. For visible, we're dropping to n equals 2. And for infrared, we'll drop to n equals 3. Now, okay, keep in mind that ultraviolet was higher energy, okay? Infrared was lower energy, and so that makes sense because ultraviolet takes a lot more of a drop, and it takes a lot more energy to promote up, and then infrared, we're not going as far, and then visible is in between those, okay? And so, these various different transitions correspond to what we see. So again, this is visible, okay, which is why it is dropping to n equals 2. And so this is the hydrogen spectra. And for hydrogen, because again, it's a single electron, it's a much simpler system, we are actually able to use that Rydberg equation I mentioned to figure out exactly what transitions are occurring to see the spectra that we see for hydrogen. Okay? Now, what do we know about the atom today? Well, we know that these quantized energy levels do indeed exist. But we also know that that planetary model that we like so much because it's easy to visualize these quantized discrete energy levels is not exactly what's happening with electrons. Electrons don't orbit the nucleus like planets. It's a little bit different than that. And so in our next section, we're going to look at the quantum mechanical model of the atom and understand that electrons are a little bit different than planets, okay? We're not going to go into like the Schrodinger equation. I'm going to mention a couple of points of it, but we're going to keep this very quantum mechanic light to just have a basic understanding of it.